Right, let's talk about C#9 records. Now, if you're watching my last video, remember that was all about value types and reference types, storing things on the stack or on the heap. And if you're not familiar with that, I do recommend you have a look at that one because we're going to assume that kind of understanding when we talk about records. And where we ended up at the end of that video was the fact that we have physical reasons to decide whether things are going to be stored on the stack or the heap, to do with memory layout, and also logical reasons. And for the most part, those two line up. But we did end with the fact that the string class is a bit of an oddity because a string has to be a reference type. It has to live on the heap because it's got variable size and therefore the memory management has to be handled at runtime. But conceptually, logically, we want a string to behave like a value, to have what's sometimes called value semantics, which is to say, essentially, that every variable we have of type string, we want to be able to regard as an object in its own right. We don't want to have the fact that two variables can refer to the same object, though obviously if string is a reference type they can. So the way that that's fixed with a string traditionally is like this. What we could have in our program is if we declare a string s1 equals hello and then a string s2 equals s1, then because string is a reference type, clearly those two, s2 and s1, are referencing the same object and we don't have this independence that we want. So there's two tricks basically that the string class does to get around this. One is strings are immutable. And all that immutable means is that there are no methods or properties available on the string class that allow you to modify its data. So you can read the data, but you can't modify it. So for example, it's impossible for us to say something like s2 square brackets 1 equals, maybe change that to a u, and we can see if we look at the error that although we've got a getter for that indexer, we don't have a setter, it's read-only. So that means that because we can't change s2, we can't accidentally change s1. And that's true of all of the methods, all of the properties that we have in a string. If ever we do want to effectively modify a string, then we have to do it by creating a new object. So what we'd actually do is say string s3 equals and then s2 dot replace, and then maybe replace the e with a u. So that will effectively achieve the same thing, but it hasn't modified s2, therefore it hasn't modified s1. It's simply created a new string with the changed data which we put in s3. Or in fact, just as often, sometimes what we'll do is, although we're creating a new object, we won't create a new reference, and so we might just say s2 equals s2.replace, and that would achieve the same thing. So that is one of the things we do on a string. We make it immutable, and then the other thing that is done with a string is the double equals operator, the comparison operator, is overloaded so that it no longer does reference comparison. So if we change this slightly, so now we've got two separate string objects that happen to both say hello, and if we do something like just console write s1 double equals s2, normally for a reference type that would give us false because they're different objects and double equals just compares the references, but with a string, because it's been overloaded, then we can see it gives us true. So that's what's done for string. And when we're writing our own data types, there may be times when we want to have a similar sort of situation where we have a data type that conceptually we would like to be a value type, but physically it makes sense that we have it as a reference type. And the example we've got here that we had in the previous video was that we had this point which is just two variables, x and y, and we decided that logically we wanted point to be a value type. And also, because it's only got these two ints, so that's 32 bits each, 64 bits in total, so that's 8 bytes, so the same size as a reference, it's not going to be a performance issue. But let's suppose we change things slightly here. Let's, for a start, just get rid of some of these methods that we've put in there for now. We'll come back to those. But let's change this by making this a double rather than int, and then also rather than having 2 dimensions, have 3 dimensions. So let's also put a z in there. And so now, logically, there's not much change. We've changed ints to doubles, we've added a dimension, but it should still logically behave using this idea of value semantics. But physically, we've actually tripled the size of that. That is now 24 bytes in size for the 3 doubles, and therefore, in terms of copying it around, that might start to become something of an overhead. Obviously, we can't be sure without doing some benchmarking, but let's assume that that's getting big enough that it might be a performance issue. And so we don't want it to be a struct anymore. So that's what we do now. We change this to this new C#9 type. We call that a record. And a record, the idea behind a record is to say it has this physical approach of being a reference type. It lives on the heap. But in terms of behavior, in terms of the semantics, it should behave like a value type. Now, one of the things that we're going to have to do for ourselves, just like we saw with the string, is that it should be immutable. And at the moment, it's not. We've got setters on those values. So we'll change those and make all of those init only. So again, if you remember the earlier video we had on this new keyword and C#9 init, this is really one of the big reasons it's in there. So now that's an immutable type, and we've declared it as a record, and that's best practice. Although you can have non-immutable records, it really kind of beats the point of what's going on. What I'll actually do here, I'm going to rename that. I'm going to call that point R for record, because I'll also put in here a couple of other data types. I will have a point C, which is going to be a class, and let's also have a point S, which is going to be a struct. So exactly the same makeup, but just so we can see the way that the 3 different ones work. You'll notice actually a little quirk in Visual Studio here. It hasn't coloured the record cyan, which it's managed to do for the class and the struct. Cyan represents data types, which this is. Just a bug, I'm sure they'll learn out fairly soon. The language, the compiler certainly understands what's going on. Let's now use that. So let's go back to our program. And what I'm going to do is simply declare a point R, so that's our record. I'm going to call it R1. And let's not do anything more with it. Now, the first thing to notice we've got there, that is a reference. And we can tell it's a reference easy enough because I'm allowed to assign null into it. So we can have that reference, we can have it as a null reference, and then we can see the IntelliSense is giving us X, Y, and Z. So we can put that in there, or we can say new and then point R, and then we could use member initializer. So let's say X equals 1, Y equals 2, and Z equals 3. So it's definitely a reference because we can put null in there. It's worth pointing out, actually, I haven't got them switched on here at the moment, but all of the things we know about nullable types, you can have a look at the video on that if you want. If we turn those on, we'll see that those rules apply to these records as well. So if I just put in a hash nullable enable on there, then we can see that if I do try to say point R1 equals null, where that is a non-nullable record, we can see that it's giving us the error there, and I'd have to put the question mark on there to make that now nullable, and so that's okay. So all the stuff about nullable references still applies to this, but I'll turn it off again because it just overcomplicates matters. So far then, nothing particularly exciting. We could have done exactly the same as that with a class or with a struct. So we've created the object. In this case, it's on the heap, and we've initialized it. But some things immediately we get for free. So let's just fill this out a bit. And so let's have a couple of those records. And then let's also, with the other ones I created, let's have a couple of structs and also a couple of classes. And then the first thing I want to show you is very simple. If I do console write of our record and run that up, we actually get a reasonably sensible toString. So remember, when we call console write, that is calling toString. And if we did that on the other types, so C1 or S1, then all we get by default is the fully qualified name of the class. So the class name plus the namespace name. So something we're immediately getting with the record is, for free, we have got this toString. It may or may not be what you want, but it's certainly better than the other default. And in fact, this is somewhat reminiscent, I think, of what we get with things like anonymous types and tuples, where they provide a default toString. We can change it though if we want to. So if we go back in here, I could, if I wanted to, in fact we've got it started there, so I could do an override of toString, and in this case all I'm doing is displaying those 3 coordinates, but with 2 decimal places of precision. So the default generated toString was just doing default precision, but if I put that in and run that up now, we can see we're getting 1.002.00. So it gives you something for free, but you get the chance to override it if you want to as well. Something else we get for free though is we get a double equals operator. So if we put in, again, let's try R1 equals R2, C1 equals C2, and let's try S1 equals S2. Well, the immediate first problem we see is that with structs, we don't get a double equals operator for free at all. We had to write one in, and that was one of the things that I had in there that I then commented out for my record. When it comes to classes, reference types, remember that double equals is just comparing the references, it's not doing value comparison. But when it comes to our record, it has auto-generated a double equals operator that simply does member by member comparison. So that will just compare X, compare Y, compare Z, and give us the result. And in this case, we can see that it's true because the X's and Y's and Z's are the same. Whereas with the class, it's false, obviously, because although they're the same values, they are different objects. If I were to change one of those, so let's change Z to 4, then we can see that it's now false because it's done the member by member comparison, and that's not worked out. So that's something we get for free straight away. We also actually get for free a equals. So I could also have said dot equals R2, and it's just the alternative way of doing exactly the same value-based comparison. You'll notice actually that there are 2 overloads of that. There is the one that takes an object, which is the one that is declared in the object base class, and that one is being overridden. But there's also another one that does take a point R. That one comes from an interface called iEquatable. So another thing we've got for free when we declare a record is, if I just to show this is happening, let's have an iEquatable for point R, call that EQ, we can assign our record into there. So automatically we've got this iEquatable, and implementing an iEquatable gives us that particular overload for equals that we've got there. So we can use equals as well as double equals. That said, of course, just like with the toString, we might want to change the way that that works. So we might want to define our own double equals. For example, when you've got doubles, you might not want to go for an exact match. You might want to have some kind of threshold as to how close they are. So you might think we could just put that back in, change those to an R, maybe change the functionality a bit. But you can see already it doesn't like it. It is saying that we've already got the double equals operator, op equality, and we can't write our own. So because it's generated one automatically, we're not allowed to change it. So we can't have a double equals or indeed a not equals. But what we can do, thankfully, is we can still change that equals method. So I could put in here, let's have a public, has to be virtual just in case we're overriding, returns a bool, and then equals, and then this is not the one from the base class, this is the one from the interface. So here I say point R, and let's just call that other, and then I can do whatever comparison I like. So actually I'll just leave it as default for simplicity. So we could say x equals other dot x and y equals other dot y and z equals other dot z. And then just so that we can see what's going on there, I will also put in just a message so we can see when we hit that. You'll notice it's giving us a warning saying that if you provide an equals, you should also provide a get hash code. So again, we've almost got that in there already. So there's the get hash code, and I'll just put the combine z on there as well. And so now we've got, well, it's exactly the same, but it could be a different way of doing our equals. And obviously enough, if we say r1 equals r2, we can see it's saying Bing, so it's going through there. But the cool thing is, if we use the operator that's provided for us, so although we can't rewrite the double equals operator for ourselves, all the double equals operator does is calls the equals method. And so if we want to change the behavior, we just change it in the one place, and that will apply to equals and double equals and indeed not equals. Again, it says Bing because it's going through that equals method. So you only need to change that one, but as we saw, also remember to do the get hash code on that. So just to summarize where we're at that point, we've created our record, we've made it immutable by making sure those properties were all init only, and that gave us for free the toString, it gave us the double equals, the not equals, implemented iEquatable, gave us various other things like that that we all got for free. We could add our own features, so we could add methods in there, we could add constructors, that sort of thing. But the thing we've got to bear in mind with all of these is make sure it remains immutable so that we don't get the reference style semantics, we're getting the value semantics. That means, of course, that we have other things that we need to do. So remember what we're saying with a string, that if we wanted to change it, we had to say something like string s3 equals s2 dot replace and then whatever it was. Similar sorts of things that we need to do with our record. So if I wanted to change a record, well, I can't do that. That's the whole point. So I can't say r1 dot x equals 27 because it's an init only property. So what I've got to do is I've got to say something like point r, r3 equals, and then I want to do this similar modification. So I could have written a method that said something like r1 dot change x2 and then put 27 in there. And so change x2 doesn't modify x, it produces a new record with that value, but that's going to become very tiresome. And so what we actually have, which is really neat, is the with keyword. So I can say point r3 equals r1 with, and then curly braces, and let's say x equals 27. So that's a nice shorthand way of saying, create me a brand new object, r3, which is a copy of r1, but change the value of x to 27. And so we can now see if I do a console write of R1 and a console write of R3, then R1 is unchanged, whereas R3 is a copy with just that value 27 changed. Or if we wanted to do more than that, Z equals 200. So I can do as many or as few of the properties, and we can see that makes the changes. So the original is not changed, it can't be, it's immutable, but we've got an easy way of making a copy with modification. So in that situation, R3 and R1 are definitely separate objects. We can see they've got separate values. What would happen though if I just said R3 equals R1? On the one hand, you might think, well, it's still going to make a copy, it's just not going to change anything. But that would be horribly inefficient. Whereas on the other hand, because this is a reference type, is it the case that R3 and R1 are referring to the same object? Well, there's a way we can actually find that out, because although we know that if I were to say console write R3 double equals R1, that's not going to really tell us, because that double equals has already been changed to give us value comparison, so that's definitely going to give us true anyway. But if you really want to do reference comparison, even though you've overloaded the double equals, then there is actually a static method on the object class called reference equals. And whatever you've done, be it with a record or a class, to change the behavior of the double equals, reference equals will always look at the references. And so if we compare R3 and R1 that way, we can see it's saying true, so that actually has not been a copy, they are the same object. Whereas if I do the with, then obviously because it's changing something, it has to do the copy, and so in that case we get false. But you may be worried, well, if they're the same object, then they're not behaving like value types, because now if we modify R3, that's going to also change R1. But of course it doesn't, because you can't modify R3 because we've made it immutable. So that's the key reason why we make it immutable, so we get this absolutely most efficient copying. Either if they are the same, it doesn't copy the value, it just copies the reference, which is efficient, and it can't be modified because we've made it immutable. Or if we do want to change it, then we use the with, and that does have to create the new object, but it gives us a neat way of doing that in concise syntax. A couple of other things to mention. One is a slight variant on the record, which is known as the positional record. So you can see here what I did was declared my point R, and then we declared these init-only properties. I can do a shorthand for that, which is simply to say public record point R, and then in round brackets straight after the name of the record, I just say double X, double Y, double Z. And basically that has generated exactly the same for me. So actually let's comment out everything in there. So we've just got this as simple as you can imagine. And that is a positional record. So it's had declared for it the three properties automatically, just the same as I had declared them there manually. And it's also done all the other things like the toString and so forth. So if we go to the program, the one slight problem we see here is that with a positional record, you don't automatically get a default constructor. So here we were trying to call the default constructor and then initialize the properties. What we now have to do, at least to start out with, it's given us an actual 3-parameter constructor taking that x, y, and z. So the slight change there, we've got to go and call the constructor. But apart from that, everything else is working in the same way. So we've still got things like the not equals and the double equals for comparison. It's still I-equatable. It's still able to copy with a with, and it still has a toString that's been defined for us so we can see what's happening there. So everything the same, slightly neater syntax. We don't have to worry about declaring these things as init only because that happens automatically. The only slight change is that we don't get the default constructor. If we want a default constructor, perfectly simple, let's pop that in there. Default constructor, but it has to call the other constructor. So we'd say this, and then the default, obviously enough, you'd expect to be 0, 0, 0. And so now, once we've done that, that means although we've still got the 3-parameter constructor, if we want to go back to the member initializer approach, which remember is okay because those are init-only properties that can be called from a member initializer, and so that's what we've got there. When you've got one of these positional records, one other thing you can do that you can't do with the manual record is it gives you a deconstruct. So you may remember from the earlier video we did looking at tuples, we talked about deconstructs. But we can see, if we take R3 there, you can see it's got that deconstruct method available. And the way we use this is we deconstruct into a tuple. So if I say something like var, and then in round brackets, x, y, and then we'll not care about z, so we'll use a discard, and then we can say that equals simply R3. And that breaks down R3, reads out its x value, its y value, we've discarded the z value, and so I could do a console write of x or a console write of y, and we'd see those values there as 27 and 2. One other thing we can do with these, if we don't have the overloaded constructor, indeed if we don't have any content whatsoever, which is still a pretty powerful data type because we've got all of these generated methods, you actually don't need the curly braces. So I could just round that off with the semicolon, and that's still a valid record. Though if we want to put other features in, obviously we need the curly braces. Last thing I wanted to show you, and one of the really big benefits we get with records, is that because records are reference types, therefore they're not got this idea that the size has to be known at compile time, and that basically means we can use inheritance with records. So remember, one of the things we can't do with structs is use inheritance. So what I could do here, I could simply say public, and let's go for, let's suppose we're going to have a 4-dimensional point. So I'm going to say public record, and I'm going to call this point 4D, and then derive it from point R, and then let's add on to that the 4th dimension, which we know is time. So we'd have a property of type double. And in fact, just remembering back to my physics days, we don't put time in there. We actually put CT, which is time multiplied by the speed of light. The reason we do that, nothing to do with C#, is so that these all have units of distance. So CT is going to give us distance, but it doesn't really matter. It's just to show us that we've got inheritance. And so now I can do something like, say, point 4D, P4 equals new point 4D, and then I could do x equals 1, y equals 2, z equals 3, and ct equals 4. And then if I do a console write of that, we can see it's generated the appropriate toString, and all the other bits and pieces that I was talking about, it's generated those as well. And so that was one of the reasons, remember, we said if you've got inheritance, you have to have a reference type, but we can still have it as one of these records, and so although it's a reference type, it's got value semantics. Other things we can do that, all the normal sort of things. So if I wanted to, I could make my base class abstract, or my base record abstract, and so we can now see that it's not allowing us to create point R's, but it is allowing us to have the derived class. Or alternatively, I can make it sealed, in which case we can now see that we're not allowed to derive from it. So all of the normal things apply, and really I think anything I haven't mentioned that applies to classes will apply to records as well. So we can have generics, things like that, all perfectly valid. So that was it. That's our look at probably the biggest new feature, I think, in C#9, this idea of the record that gives us an easy way to have value semantics on something that's actually a reference type. It was something you could do before because it was done with strings since the very beginning, but it was something that was a bit fiddly. Here it's been made much, much easier. So I hope you enjoyed that. If you did, do click on the like button, do subscribe, and I'll see you next time.